Now, statistics is how you collect, organize, and analyze data to come to accurate conclusions from your data set. So welcome back to the channel and welcome back to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. Today is day 45. Yeah, sorry, today is day 46, if I'm not mistaken. So we're on the course called Introduction to Statistics in Python, and we're on the second chapter. This is the seventh course out of the 9 courses in the Python for Data Analyst career track on the DataCamp platform. We are on the seventh course called Introduction to Statistics in Python, and we're on the second chapter where we are looking at probability and random numbers generators. So we are looking at how to generate random samples and measure chances using probability. And we're also working on a real-world sales data set to calculate the probability of a salesperson being successful. So that is what we have been doing over the past couple of live streams. So the goal of this live stream is to learn and master Python 1 hour daily over the next 100 days. So that is like a compound interest or compound way of learning. So I'll just go ahead and share my screen to continue from where we stopped on day 45, where we're actually looking at what is called a discrete. No, we're looking at So we're looking at our continuous distribution from day 46 here that we did, and that was yesterday. So we are still on chapter 2 of the whole career track, and we actually we perform analysis using continuous distribution and created random numbers using this histogram or spots like this. So you can catch all of this on day 45 of the live stream. So if I go ahead, we're on binomial distribution. So we've covered what we called discrete distributions. We've looked at continuous distribution. We are now on the final lesson here, which is of binomial distribution, simulating sales deals and calculating binomial probabilities. So along the line, we also learned how to calculate a discrete distribution and continuous distribution using probability and chances. So you can just go ahead and watch the previous live stream to understand all these concepts in this lesson here. So all the data set, also exercise files that we are using, this data set that we use for each lesson is linked under the YouTube description. So do make sure to download those data sets and practice along with me. So without any other delay, so let's look at what is called the binomial distribution in Python.
It's time to further expand your toolbox of distributions. In this video, you'll learn about the binomial distribution. We'll start by flipping a coin, which has two possible outcomes, heads or tails, each with a probability of 50%. This is just one example of a binary outcome, or an outcome with two possible values. We could also represent these outcomes as a 1 and a 0, a success or a failure, and a win or a loss. In Python, we can simulate this by importing binom from scipy.stats and using the binom.rvs function, which takes in the number of coins we want to flip, the probability of heads or success, and an argument called size, which is the number of trials. Size is a named argument, so we'll need to explicitly specify that the third argument corresponds to size, or we'll get incorrect results. This call will return a 1, which will count as a head, or a 0, which will count as tails. We can use binom.rvs 1, 0.5, size equals 1 to flip one coin with a 50% probability of heads one time. To perform 8 coin flips, we can change the size argument to 8, which will flip one coin with a 50% chance of heads 8 times. This gives us a set of 8 ones and zeros. If we swap the first and last arguments, we flip 8 coins one time. This gives us one number, which is the total number of heads or successes. Similarly, we can pass 3 as the first argument and set size equal to 10 to flip 3 coins. This returns 10 numbers, each representing the total number of heads from each set of flips. We could also have a coin that's heavier on one side than the other, so the probability of getting heads is only 25%. To simulate flips with this coin, we'll adjust the second argument of binom.rvs to 0.25. The result has lower numbers, since getting multiple heads isn't as likely with the new coin. The binomial distribution describes the probability of the number of successes in a sequence of independent trials. In other words, it can tell us the probability of getting some number of heads in a sequence of coin flips. Note that this is a discrete distribution, since we're working with a countable outcome. The binomial distribution can be described using two parameters, n and p. N represents the total number of trials being performed, and p is the probability of success. N and p are also the third and second arguments of binom.rvs. Here's what the distribution looks like for 10 coins. We have the biggest chance of getting 5 heads total, and a much smaller chance of getting 0 heads or 10 heads. To get the probability of getting 7 heads out of 10 coins, we can use binom.pmf. The first argument is the number of heads or successes. The second argument is the number of trials, n. And the third is the probability of success, p. If we flip 10 coins, there's about a 12% chance that exactly 7 of them will be heads. Binom.cdf gives the probability of getting a number of successes less than or equal to the first argument. The probability of getting 7 or fewer heads out of 10 coins is about 95%. We can take 1 minus the probability of getting 7 or fewer heads to get the probability of a number of successes greater than the first argument. The expected value of the binomial distribution can be calculated by multiplying n times p. The expected number of heads we'll get from flipping 10 coins is 10 times 0.5, which is 5. It's important to remember that in order for the binomial distribution to apply, each trial must be independent, so the outcome of one trial shouldn't have an effect on the next. For example, if we're picking randomly from these cards with 0s and 1s, we have a 50-50 chance of getting a 0 or a 1. But since we're sampling without replacement, the probabilities for the second trial are different due to the outcome of the first trial. Since these trials aren't independent, we can't calculate accurate probabilities for this situation using the binomial distribution. Time to explore binary outcomes using the binomial distribution.
Interesting. This is like a much more technical concept of binomial distribution. So let's see what we need to do here. So we have this our data sets. So we're actually using the sales data food consumption data sets. So we generated some random probabilities here also. But let's follow the instruction and see how to solidify the concepts. So I want to simulating sales deals. Assume that a male usually works on 3 deals per week, and overall, he wins 30% of deals he works on. So each deal has a binary outcome. It's either lost or won. So you can model his sales deals with a binomial distribution. So in this exercise, you help a male simulate a year's worth of his deals, so he can better understand his performance. So NumPy is imported as NP. So import binom from SciPy. So we need to import binom. That's another library. So you say from SciPy the stats import binom. So these are part of the library we use to work. So we learned all about a lot of library now. So we learned all about pandas, NumPy, or matplotlib, or SciPy.stats, where we use uniform. And we're now using this binom. Interesting. So let's continue. So I'm going to set a random seed to 10 import binom from scipy.start and set the random seed of 10. So that's going to be np.random, np.random dot seed. So that will be 10. Okay. Let me give it a shot here. Okay, let me see. I could just copy everything and paste it in my Jupyter notebook. Okay, so I want to recreate same scenario in this situation here. So let's see how to do that. Okay. This is better. So I could just run this line of code. So it works fine. What I could also do is just rerun the whole code from scratch. Okay. So then we set a random seed of 10. Okay. So we set a random seed of 10. The next thing is to simulate one deal worked on by Emil, who wins 30% of his deals he works on. Okay, we're going to use binom.rvs for this. So that we're going to be using binom.rvs for that. So the binom.rvs. So we want to simulate one deal. So we want to simulate one deal. One. That's the number of coins, probability of edge of success. So 30%, that will be 0.3. 0.3. And the size is 1 also. So let's run the code. So we get the answer of 1. So next to simulate a typical weeks of Amil's deals or 1 week of 3 deals. So let's give it a shot here also. So I expected to get just array of 1, which is correct. Then the next thing we need to do is to simulate a typical 3 weeks of Amil deals or 1 week of 3 deals. Okay. One week of 3 deals. Final.rbs. open brackets. So one simulates 1 week of Amil deals where he works on 3 deals per week with a 30% chance of winning each deal. So that would be the number of will be 3. Then the chances of winning, the probability of success, either one or deal is there, that is 30%. Probably is going to win the 3 deals is 30%. Then the size equals to 1 also. So let's run the code. So I'm still going to get 1. So that means probably he won 1 deal out of this. But let's see the result we are going to get in my Jupyter notebook here. So this week he didn't win any day. So the chance of that, so this idea is that in a single week, in a week where Emil plays 3 deals, so he did 3 deals. So the chance of winning is 30%. So the results we are expect to be getting is that we get 0 where he won no deals, 1 where he won one of the deal, or 2 where he won 2 deals, or 3 where he won all 3 deals. So in my instance here, since this is a probability test, I'm getting 0. That means he won none of the deals, but I'm getting 1 here, which is the same result. So now I want to simulate a year's worth of Amil deals or 52 weeks of 3 deals each and store in deals. That means I want to simulate 52 weeks, but for each week he's doing 3 deals and he has 30% chances of winning 3 of the deals. So let's do that. That's probability in action. Now we binom.rvs. So the chances that is going to win is doing 3 deals per week. The probability that is going to win is 30%, that is 0.3%. Then the size is for 52 weeks. Size equals to 52 weeks. So print the mean number of deals you want per week. So once it's the mean number of deals you want per week, that'll be deals dot mean. Let's see. I copy this. Let's run the code. So the mean is 82%. Number of deals we want per week based on this simulation we did here. Let's do the same thing in this instance here. If I call on deals, so I expect to have just multiple numbers. This week he won 1 deal. So this is total deals he won in a week. He won 1 this week. Next week he won another 1. This week he won 1. This week he won none. You get it now. If I print the meals of deals, a meal is winning. Let's see what I'm going to have here. 84% chances. That's interesting. So brilliant binomial simulation. In this simulated year, Amir won 83% deals on average each week. That's high. So calculating binomial probabilities. Let's see. So this is the second thing we need to do here. So just as in the last exercise, assume that Amir wins 30% of the deals. He wants to get an idea of how likely he is to close a certain number of deals each week. In this exercise, you calculate what the chances are of him closing a different number of deals using the binomial distribution. So what's the probability that Amil closes all 3 deals in a week? So probably that he closes all 3 deals in a week is kind of okay. Let's see. Let's see how we do that. Probably I close all 3 deals. Definitely that will be 100% probability. Probably binomial. Okay. Binomial is important, so binom dot RVS, open and close brackets. So since the number of deals is gained per week is 3, number of deals is gained per week is 3. So we want to see the probability of him closing all 3 deals. So that means this is going to be 3. Number of chances of him winning the whole deals will be 30%, which is 3. And probability that is going to win all 3 deals is 30%. This is 0.3, and the size is 3. So let's see. That is 4. Interesting. So probability of him closing all 3 deals. So I think probability of closing all 3 deals. We should have, what should we have here? We have 4. That's interesting. Ooh, we didn't get that. Okay, let's get help on the error. Okay, I'm not using binomial.b. I'm supposed to use binomial.pf here. I'm going to using the binomial probability mass function, calculate probability of, let's see, is none. So telling that it's going to close all 3 deals, closing 3 out of 3 deals is none. Wow. Oh, okay. For PMF, the functions are different. Okay, so I expect to get 3, not, it's going to be 3, 3, 3. So it's interesting. So this is 30%, closing 3 deals. So for binomial.pmf, so the functions are number of heads, number of trials, probability of heads. So number of deals is 3, number of trials is 3, probability of winning all 3 is 3. That's why we are getting the result here. Okay. Ooh, why am I getting an error over and over again? Let's see. And this should be 0.3. Probability of success is 30%. This should be 0.3. That is over 26% of closing out 3 deals, or even less than 2%. So I'm expecting 0.3 here. You can see that is 0.2%. Interesting. Oh, we know that. So I go back a little bit. So what is the probability that Amir closes out 3 deals? So our result is 26% probability that he closes out 3 deals. Okay. Now let's move on to the next question. Then I say, what's the probability that Amir closes 1 or fewer deals in a week? That'll be 1 minus, definitely